Hello everyone, welcome to our workshop. Today we'll talk about reinforcement learning. Our speaker, Tyler Suard, will be with us. He's an AI specialist. Before we start, I want to talk about our company, Magnimind Academy. We founded in 2015 and we've been teaching data science since 2015. We have three different main type of programs. Our full stack data science bootcamp, our one-on-one machine learning project mentorship bootcamp, and our mini bootcamps. In our full stack data science bootcamp, we teach the theory and the hands-on experience. And at the end of the bootcamp, the aim is to find you industry jobs. In our one-on-one machine learning project mentorship bootcamp, it's for the ones who is aware of the theory, but who needs guidance and building portfolio. And our mini bootcamps, where you can learn different subtopics of data science with different modules. Right now, our machine learning mini bootcamp is starting on February 18th. It's for 4 weeks, 12 hours, and it's for free. You can join it online. The on-site participation is full right now. You can check our website, magnimindacademy.com, to learn more about our programs, or ask to me to April at the end of the meetup. We are organizing a lot of these events. You can join all of them. You're always welcome here. Having said that, I want to announce Tyler with a round of applause. Thank you.
Everybody, thank you guys so much for having me. I'm really excited to be here. April messaged me a couple weeks ago and she said, hey, would you like to give a talk? And I was like, sure. And all these people signed up, and I'm really grateful to you guys for coming out on a Saturday to hang out with me. So we're going to talk about reinforcement learning, and I'm going to tell you why this is so exciting. Like, I didn't even know about reinforcement learning until maybe like 2 months ago. And before that, I thought artificial intelligence was just classifying pictures of cats or maybe grouping things together. And that was exciting to me, but this is way better. Okay, so for the people who aren't super technical, I'm going to go, from a foundation and work up to reinforcement learning. Artificial intelligence is getting a computer to do something that normally requires human thought. For instance, driving uses artificial intelligence because you're moving a car, and that normally requires a human brain. Machine learning is a type of artificial intelligence. Instead of specifically programming a computer to do something, you give a computer a set of data and you tell it to train itself on that data. It's like giving a very smart child a textbook and saying, here you go, learn on your own. So a specific type of machine learning is deep learning, where you just have your inputs and you have your outputs, and then it creates a function that connects them. So like on your left, you have the number 3, and on the right, you have a number 6. And then a deep neural network tries to put those two together and says, okay, how do we turn a 3 into a 6? We can either add 3 or we can multiply it by 2. And so if you have a bunch of inputs and a bunch of outputs, it learns from those. Okay, so reinforcement learning is kind of different from those things because it's teaching a computer to accomplish a goal using rewards and punishment. Okay, so now we're going to talk about why. Why is reinforcement learning so cool, and how has it been used recently? We're going to talk about how it's done as far as the concepts go. We're going to talk about what I believe the future is for reinforcement learning. Okay, so this company called DeepMind recently, actually you can look up this this documentary on Netflix. There's a surprising amount of drama behind this. So AlphaZero is a program created by DeepMind that beat the world's best player at a board game called Go. So this is Lee Sedol. He is the world's best player at a game called Go, and he actually ended up giving up playing Go because of this, because he was beaten by a computer. And this guy over here, he is just somebody with a computer screen. He just made moves that the computer screen told him to. So DeepMind trained AlphaZero. Oh, shoot, my computer is talking to me. Okay, so I'm hearing like some echoes of my voice. Okay, so DeepMind trained AlphaZero using a bunch of data sets of humans playing AlphaZero or playing the game Go. So what they did was this machine was trained using examples of humans playing this game. So the machine learned to play a game from humans, and then the machine was used to beat humans, which is pretty cool. I think that's that's pretty cool. But what's even more interesting is a few months after this happened, they came out with this computer program called AlphaZero. And why this one is so interesting is because there were no humans in the loop. It was not trained on data of humans playing games against other humans. It was trained by playing the game against itself. It played against itself millions and millions and millions of times, and eventually it became a better player than AlphaGo was. It was able to beat AlphaGo 100 times in a row. There was no human data, there was no real world data put into this loop, but still it worked in the real world. I just think that's so cool that you can train a machine on synthetic data in a simulation and then have it work in the real world. And there are tons of advantages to this. Like with deep neural networks, you need a ton of data. And sometimes it's hard to find that data. Like if you want to figure out the connection between tire weight and duration, that data might not be available online. And if it is, it might be collected by people who make mistakes, or it might be rounded up, and sometimes you can't trust that data and it's really hard to use. But synthetic data is generated by the computer, so it's perfect. It's quickly generated, and you can delete it as soon as you make it. So you don't have to work with these huge data sets because it's always streaming through the neural network. And it's easy to make, and it applies to the real world, which is super cool. Okay, so OpenAI is a nonprofit that was started by Elon Musk. He is afraid of AI's potential, and so he wanted to create a nonprofit that puts AI moving in a good direction. So recently, OpenAI bought this really expensive robot hand. It's like $100,000. How much is the shadow hand? Do you know?
It's around there.
Yeah, really expensive robot hand. And they wanted to solve a Rubik's Cube. So instead of training it in the real world, what they did is they made a simulator of this hand. And they had this hand work in the computer in a simulation on a Rubik's Cube. And they trained that hand for millions of years. I mean, in our time, it was only like maybe 2 weeks or something like that. But they had like 100 simulations of this hand going, and they had it going at like multiple times speed. And so what they did was they had one model that was training on all of these thousands of versions of this hand going at multiple times speed. And so this hand gained millions of years of experience using this Rubik's Cube. And then they took that model and they put it into an actual real robot, and it actually worked, which is super cool. Okay, so, all right, so this is really cool. You guys should definitely watch this video because it's awesome. Okay, so in 2017, OpenAI, that nonprofit that we talked about, it defeated the world's best DOTA players. DOTA is a video game where you're in an arena and you like click on the bad guys and then you cast spells and then you defeat them, right? So this was a really complicated task for a computer to learn because there's so much long-term and short-term strategy, and you got to move your guys here and there, and you got to attack as a team, and you got to cast certain spells. And so it took a lot of time to train this. I think somebody estimated that it took $800,000 of computing time to train this model. And what it did is, again, there were no humans in the loop when it was training. It was just the computer playing against itself and learning how to play this game to get better at it. So these guys are not very happy. These are the world's best, the world's reigning human champions at DOTA. They're called OG. They're very famous in that circles. It's really interesting. Like they have these huge esports tournaments, and there's this whole underground world that I didn't even know about surrounding this game. So they were pretty upset when they got beat. They got beat both times when they tried to fight the computer. The first time it was kind of even, and the second time they just got slaughtered. The computer could do these things at like microseconds that no human could. Like a computer would run into battle and it would attack and attack and attack. And then it would know exactly the moment to turn and run away where it wouldn't die. And so the humans were really, really frustrated because the computer would come and attack and then run away, and they couldn't hit it enough to kill it. Whereas humans don't have that split-second calculate exactly how much life I have and then run away if I need to. And so the enemies would run away and then they would heal and then they would come back and attack. And so they just had tons of cool stuff like that, tons of strategy that human players couldn't have. So an interesting thing about this is this was very publicized. Like this was a really big event, lots of sponsors and everything. And then after, people watched the YouTube video and they said, oh, you know, they weren't doing a good job. Those humans, they were doing a terrible job. I would have done this. I would have done that. I could have beaten that computer. So OpenAI said, okay, well, we're going to open up our bot online and you can play against it. More than 10,000 people played against this machine, and the machine won 99.4% of the games, which is pretty cool, I think. I mean, this is a machine that was trained fighting against itself, not against humans, and it beats humans 99.4% of the time, which to me, that's like an innovation. That is something that needs to be looked into more. Okay, so now we are going to talk about how does reinforcement learning work? Okay, so the idea for reinforcement learning came from experiments with mice and mazes. I think everybody knows this one. You got mice at the start and you got food at the end, and you try to train mice to navigate through the maze. And then over time, mice get better and better at navigating this exact same maze. They learn. Okay, so we're gonna do a funny little example. I'm going to stand right here and I'm gonna take off my glasses so I can't see. I need someone in the front row to raise their hand, and don't tell me who it is. Just one person. Okay, do we have one person? Okay, good. Now put your hand down. Okay, now everybody else in the class, we're gonna do a reinforcement learning experiment. When I step closer to this person, I want you to clap once, because that is my reward, right? And if I don't step close to that person, just do nothing. If I step in the wrong direction, do nothing. If I step close to them, clap once. Okay, ready? This guy? Yeah. Yes. All right. Round of applause for yourselves. Good job, guys. Okay. So you see what we did there? You communicated to me a complex set of instructions using nothing but a reward. And that is what reinforcement learning is. You communicate very little to the computer, actually, except for rewards. The environment is already set up, just like this classroom is set up. There are all these people in it. And you just tell the computer what behavior you want it to do. And sometimes you give it negative rewards for behavior that you don't want it to do. Okay, so these are the components of a reinforcement learning experiment. There's an agent, which is me. That's the brain. That's the computer that you want to learn. Okay, the goal, which is set by the person who is running the experiment, this gentleman right here, is the goal. And one thing you could think about it is kind of a roundabout way of achieving a goal. Like, you could just program me to step left 5 times, but that wouldn't generalize. Because let's say we ran the experiment again and you guys picked the gentleman over there. I would step left 5 times again. And I would just stay here and you would say, no, we want you to do this. And that's what reinforcement learning is. You can't just program individual actions. You have to get the computer to learn on its own, because then it can generalize to the real world. You can open up and let your baby bird fly, as opposed to, programming your baby bird to do one thing. So, all right. Okay, reward, that's the clap. It's set by you. And Pablo Escobar in the show, what was it called? Narcos, yes. He said that he gives people the silver or the sword. As in, if he wants you to do something for him, he says, I will either pay you or I will kill you. And that's kind of what rewards are like. You can give them a reward, silver, or you can take away a reward. And computers take them very seriously. Okay, so this room is our environment. It is all of the places that I can be. Like, I can be here, I could be here, I could wander around the back, I can go wherever I want to. That is the environment that the agent is in. And a state is a particular spot in that environment. Like right here, this is a state. This is where I started out. This is a state. This is a state, right? It's kind of like being in a state of mind, like I'm happy right now or I'm sad right now, except it's like reality. It's a real place where you are. Okay, so actions, pretty straightforward. In any environment, you set the actions that your agent can take. So in this particular environment, the only actions that I could take were I can move right or I can move left. So, and reward function is total rewards over the entire match. So I don't know how many times you guys clapped, probably like 6 or something like that, but that would be my total rewards or my rewards function. Okay, we're gonna do another experiment. You guys are sitting in class, in a class full of people, and you start to nod off. You didn't go to bed at an appropriate time. You didn't have enough enough to eat. So you start to nod off, and now you are in a dream world. You wake up and you are on a chessboard. This is so weird. You are in this space right here, and you can't see anything else except for this tower over here, this mysterious, ominous tower. Okay, so you're kind of freaked out, and you're like, okay, I gotta get off this chessboard, and I gotta get back to class. So you move left. Nothing really happens. You move left again. And you're saying, man, I ran into a wall. There's no place else I can go. Okay, I'm gonna try moving up, see what I can do. Boom. Okay, so all of a sudden, a piece of cake gets launched from this tower, and it lands in the square where you are. You're a little sketched out. You're like, well, where did this cake come from? That's kind of weird, but it looks really good, so you eat it. And you're like, oh my God, that was the best cake I've ever had in my life. That was so good. I really want that cake. Where should I go? And then you go up. Oh, you got another cake. Oh, this is so good. So you keep going up. You keep getting more cake. And you're like, this is so delicious. I really, really want to keep eating this cake. And you get up to the top. You turn right. Yes, more cake. This is amazing. Yay, cake. Yay, cake. Yay, cake. All of a sudden, no cake. What's going on? Why isn't there? Why am I not getting any cake? And so you say, okay, I'm going to turn down. More cake. Boom. Yes. Life is good again. Life is good again. No cake. What's going on? I don't understand. Where's my cake? So then you go back, you backtrack, and then you find the goal. You see, so the person, whoever's in this tower, I think of him as like a little old man who launches cake. He was giving you a slice of cake every time you moved closer to the place that he wanted you to go, right? And that's what reinforcement learning is. We set a goal, and then there's this little clueless little agent guy here, and we control his behavior by giving him rewards, but we're also a little bit hands-off too, because we want him to learn how to get to the place on his own, right? Okay, so you wake back up, you're back in class, and the only thing in your mind is the actions that you took to get to that goal. You went over here, then you went up, then you went down, and that is called your policy, right? Think about Walmart. Walmart has a return policy. Walmart is unlikely to let you return regurgitated food. I asked, believe me. Walmart has a goal. Their goal is to earn money. Their policy is the actions that they take in specific situations to make sure that they earn money, right? I don't think it's specifically in their manual, but the situation is somebody's trying to return regurgitated food, and the action is no, and the goal is earn money. Okay. So, you fall asleep again. But this is a different scenario. You don't get any rewards except at the end. This is a lot more like a real scenario. If you were playing chess with your best friend, you don't get a reward for every move that you make. You only get a reward when you beat your friend, right? Like nobody's going to pat you on the back for moving your pawn. Nobody's going to say, oh, good job, you just moved a pawn, congratulations. They'll pat you on the back and they'll say, wow, you're really smart if you win the chess game. So how do you get a computer to play a game like this, where there isn't really any reward and they're probably going to move around randomly? Okay, so it's something called the Bellman equation, which I'm not going to go into, and it's something called iterating a value function, which is all of this complicated math. So I'm just going to kind of summarize it a little bit. So let's say you are here on the bottom. You cannot see this cake, but it is a freshly baked, warm piece of cake. How else would you be able to find this piece of cake? Yeah, by smelling it, right? So let's say where the cake is a 10 on the smellometer. And then radiating out, it's lower and lower smells. So if you want to find that piece of cake, would you want to move away from the smell toward less intense smells, or would you want to move towards more intense smells? Right. So in this rule, for this, it's called a value function. We want to be moving toward more and more awesome states. We want to move from where we are to state 6, and from there to one of the state 7s, right? I'm going to move left. And from there, we want to move to state 8. We always want to be moving in the direction of a state that is a higher value than the one we're currently in. Or we want to be moving from where we are, our current state, to another state where there's more of a cake smell, because then that means we're getting closer to the cake. And we go up there, and ta-da, we got the cake, huzzah. Okay, So one thing that I want you to notice, this isn't the only way to get to the cake. There's this policy. There's another similar policy. There's another policy. All those policies are from the same position getting to that cake. So there's not just one way to do it. Okay, here's another really, really interesting topic, and it's super important to understand as far as reinforcement learning goes. Why wouldn't something just get stuck in a corner and stay there? Because greed versus exploration. You can set how curious your agent is going to be. So imagine you are a baboon. You are on the plains on a savanna in Africa, and you know that you can shake trees and bugs will fall out of them. So you walk up to this tree, you shake it for about 5 minutes, and you get a nice bug and you eat it. So you can stay with this tree and you can keep shaking it, and you can get a bug about this size every 5 minutes, or you can look for a better tree. You can look for a bigger tree that might have more bugs in it. So let's say you find another tree and you shake it for 5 minutes, and out comes this huge bug and this other bug. So you get 2 bugs, and one of them's even bigger. This is awesome. And this is why you do exploration. So what you can do is you can set, it's called Epsilon, which is the fraction of the time that the agent will explore versus exploit, right? So let's say 20% of the time, like, let's say I were to beg for money from everyone in the front row. I walk up to this gentleman right here and I say, give me $20, give me $20, give me $20. And every time I say that, maybe like 1 in 100, he'll give me $20. So I can just stay here and say, you know, give me money, give me money, give me money for the rest of time. Or like in this one, it says 80% of the time I will exploit, and then 20% of the time I will go explore. So 80% of the time I'll be asking you for money. Then I come over here just to explore for 20% of the time. You don't give me any money. So I come back here, keep exploiting you. Then maybe I come over here and you give me even more money. So I stay here and you're the new exploit. You're the new person who I'm exploiting, right? This is what I do in my real life. Okay. So Epsilon sets the percentage of the time you want to explore versus exploiting the best that you already know. Okay, so now we're going to talk about deep reinforcement learning. What we just talked about, there wasn't any deep learning going on. It's actually, you can just do it with math, very, very complicated math. But this is really cool, and this is where it gets interesting. This is where it gets into the OpenAI stuff with DOTA and all the games that we talked about. This is actually incorporating deep neural networks. This is a video of what a deep neural network looks like when it's in action. And so this is kind of what deep neural networks do. You put in a picture of a cat, and then it puts out the word cat. And then you put in a picture of a dog, and then your output is the word dog. And like I said previously, a neural network maps the inputs to the outputs. It learns what kind of an output you want when you get a certain input with the hope that it will generalize. As in, if we put a different picture of a cat in here, it's still going to say cat. If we put a different picture of a dog in here, it's still going to say dog. And how it trains itself is you tell it that you want it to maximize the accuracy. You give it training and test set, and then you test it, and it shifts what's going on in here until the accuracy is maximized, right? So you have your inputs, your outputs, and a number that you want to make really big, right? So like 90-something% is great for accuracy. I'm seeing a lot of puzzled looks. Is there anything else that I need to explain about this? Yeah.
Is this what we're hearing about in the news, that we are unintentionally teaching computers racism and bias? Because it says, oh, you lock a bunch of Arabs, you lock a bunch of African-American people. I guess that's what I should flag at the airport or in criminal algorithms. Or am I using the wrong model?
No, I mean, that's kind of the same thing, but it's also different. That's not something that I'm an expert on, you know, racial bias and algorithms, so I can't really speak to that. But it kind of is. I mean, deep learning is really, really widely used right now. This is kind of what everybody's doing, because every other type of machine learning you can do with deep learning. So it kind of just, it approximates equations. So, all right. So deep reinforcement learning is similar because it has an input, it has an output, and it has a number that you want to maximize. So instead of having a photo of a cat and then the word cat, you have your state, right? And then you have your action and your neural network, and the neural network tries to maximize rewards. So just for an example, I'm right here. I'm a neural network. I'm standing in this state, and I have actions that I can choose. I can choose left or right. Given my past experience, going left will give me more rewards. And that's what the deep neural network tries to do. It gains from experience to increase rewards. Okay, so quick quiz, you guys. So if the agent is in this state right here, here he is, and here's the goal, and he will get more rewards the closer to the goal he is, which direction will the agent move?
Right.
Yep, he's gonna move right. Very good.
Does the agent understand that? Does it just have to pick one step, or can it tell that it's stronger smell than right than going down?
Well, that's a good question. Actually, the smell thing that I talked about, the value function, does not apply to deep reinforcement learning. So in this situation, the agent would have to learn through trial and error, through going through completely randomly all around until it hits the goal, and it would learn which way will give it the most rewards. All right. Okay, Atari games. This is really fun. I actually did this on my computer. So this is a game called Space Invaders. I know that nobody in this room remembers it, but there's a little spaceship down here, and it shoots aliens, right? And they explode. And it's really difficult, actually. I have tried playing this game, and it is very, very hard. So the state is everything on this screen. Like we talked about states. It's like a square that I'm standing in for me or for the chessboard. But in deep learning, it's a little bit more complicated than that. The state is this screen, but the features get extracted from it, right? So we use a convolutional neural network, which don't worry about it, to extract the features like the number of lives, the number of aliens and where they are, the spaceship, and all of these little fortresses in your score, right? So that is your state. Everything on this screen becomes your state. Then the actions that you can do are you can go left, you can go right, or you can go pew, 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 shoot the bad guys, right? So this is just like the reinforcement learning experiment we did in this room. So here is how a deep neural network does this. Deep neural network looks at the state, right? It sees where everybody is, what lives we have, etc. Then the deep neural network chooses an action based on its experience in order to maximize the reward. The reward is, for this one, is your score. All right. And then step 3, the player's action changes the environment, or the environment could change itself, right? When the player acts, when the player goes pew, 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 it shoots the bad guy, right? And they explode. And now the state has changed, right? The environment has changed. Like, let's say I'm up here and I'm getting into a fist fight with somebody. Like somebody swings at me. My mind tells me, okay, I can either punch or I can duck. And I say, okay, he swung at me, I should probably duck. I duck like that. So then I'm standing up here and I think, okay, I can either duck again or I can punch. And so my mind says, I'd better punch this guy because if I don't, he's gonna swing again. So I choose the action punch. Then the guy is lying on the floor, right? He's knocked unconscious. The state has changed. The state of the room has changed. The environment has changed because I no longer have an enemy. And then my mind says, okay, we're good. We don't have to fight anymore. All right? Does that make sense? Okay. All right, so
Is the reward in there the score, the actual score?
Yes, it is. Very good question. Yes, the reward for this specific game is the function. Yes, or is the score. Yes.
When you're training with sparse rewards, or when you don't have a reward for every single action that you take, then how do you proportion your reward to specific actions so you can train your network?
That's a really good question. From what I understand, it's kind of more of an art form rather than a science. You have to do trial and error because, let me show you this next slide, because if you set the rewards wrong, then, you know, this guy will keep bumping into the wall. And if you set it like say, let's negative 0.5 reward, then it might stay away from the wall. But if you do it like a negative 1,000 reward, then it's going to be really confused. It's going to be like, what did I do? So yeah, you have to do a lot of trial and error as for what rewards you want to give or disincentives you want to give. So, all right, so this is one thing that's also really fun. This is a 3D designer called Unity. They make a lot of video games in it. And so what they did is they said, okay, we want this blue guy this blue cube right here, we want it to push this orange cube across the line. And this is one of the first training episodes they did. And obviously it's terrible at it, right? But after 20,000 iterations, it got pretty good. So basically, deep reinforcement learning is you have your environment and you have your agent, right? The agent is the little blue guy, and you hook up a deep neural network to the agent so it can learn. And then it executes random policy. It makes completely random moves. Like you can tell that this is obviously very, very random. It does random moves until it gets something right. It does random moves until there's a reward, right? And then it tries to repeat those moves. And that's how deep reinforcement learning works. Acting completely random until it gets a reward and it's like, oh, I like that. And then it tries to imitate that behavior next time and then get more and more rewards as time goes on. Okay. Okay. This is really cool. This is why I'm really excited about this. It's scary, but it's awesome. Okay. So reinforcement learning, we've already seen it's really powerful. I think reinforcement learning is going to be used in military strategy because as we talked about, reinforcement learning was able to beat 99.4% of all humans. So real life safety of our families and our country is way more important than a video game. There's no excuse for us not to use this, not to use artificial intelligence to defend ourselves. So my thought is maybe there's like a general in charge of an army and he says, okay, we're going into battle. How do I do this? A computer runs simulations and tells him, okay, these are your units. These are the enemy units. This is the best way to win. So they go around the back, they do whatever, they obey the AI strategy and they fight an unbeatable battle. They win or they fight an unbeatable offense. Okay. So after that, military units controlled by artificial intelligence. There are a lot of advantages to this, particularly with jet fighters. With jet fighters, if you swoop too fast or if you turn too fast, you lose consciousness because all the blood drains from your brain. But an AI controlling a plane does not have that problem. So, and also it has faster reaction times, which is really interesting. As we talked about with the, with OpenAI using DOTA 2, there were like sub-millisecond calculations and reactions to like get into and out of battle that humans cannot do. So my thought is the future will be military strategy controlled by artificial intelligence and also military units controlled by artificial intelligence because it will be incredibly effective, and two evenly matched forces, a human controlled force will be completely destroyed by one that is controlled by artificial intelligence. And if you guys are fans of science fiction, that is exactly how the movie Terminator happens. We give control of our military over to an evil AI and it decides to kill all humans. So I don't think that part's gonna happen, but I do think that this is gonna happen. So I think we're safe. Thank you guys for listening. My name is Tyler Suard. I'm an artificial intelligence specialist. If you guys want to contact me, my email is tylersuard@gmail.com or tylersuard.com. I do run a Slack group online. It's like a mentoring group. People who have questions about machine learning, they can ask me questions or ask questions in the group. So if you would like to join that or be part of it, come and talk to me afterward and I'll try to get you set up. Thank you guys very much for listening. I really loved being here. And time for questions as well. Yes, sir.
You point out that you can, a computer can train and defeat people. Can we train a computer to say, defeat that cancer, defeat that bug, defeat that virus?
Eventually, yes. But maybe I don't really know how to answer that question. We can look that up afterward if you'd like. I mean, because in the real world, like in fighting bugs, there are a lot more. You would have to set up the environment just right, like on a submolecular level. Like the simulation would have to be accurate to cancer cells. So, yes, sir.
Yeah, so there are a lot of RL algorithms like DBG and there's like model 3, model base. There's just like so much out there. So to really get started in reinforcement learning, what do you think is a good one to start with?
Well, I can't. Oh, the question was what reinforcement learning algorithm to get started with. I can't speak to specific reinforcement learning algorithms. I can say that some experiments are really good to start out with, like OpenAI Gym is a really good project to get started with, or the one that I was doing with Unity is called Unity ML Agents, and both of those have some pretty good tutorials. They're difficult to install, but after you've installed them, they're pretty easy.
OpenAI Gym uses.
Okay. Sir, you had a question?
Yeah, in the deep learning example, the agent, the blue agent pushing the orange. Is the agent aware of the overall environment?
Yeah, actually, so in that particular example, Unity uses what's called ray casting. So you sort of imagine if you have two poles sticking out of your eyes and they go like maybe like 10 feet and you can only detect what those poles touch. Like, so if I go over here, I detect it, oh, that's a chair, that's a chair. So it's not like really sight, it's kind of like more object detection in that specific scenario. So they are aware of the walls and they are aware of the objects around.
The crosses with it pushes by heuristics. It finally pushes the orange block over into the checkerboard. It gets its reward, and thereafter it knows that the goal is to get that orange block past the line.
Yes. Yes. Next question. Yes, sir.
Yeah, so I was gonna ask about Epsilon.
This guy's my boy. He gave me money when I needed it.
Exactly, so you gotta pay me back now.
That wasn't part of the deal.
So I understand you say Epsilon determines how much the agent's gonna explore or exploit. So when you say that value is like a percentage, is it the percent to explore or is it the percent to exploit?
I think exploitation comes first.
Okay.
I think Epsilon is the exploration. Shoot. Yeah, I'm not sure. I'm sorry. We can look it up afterwards. I think Epsilon is the percentage of the time that you explore. So, yes.
Back in 2015, DeepMind
Yeah.
did a good job making the software game beat the human players. But my understanding is they didn't do a good job after that, how to utilize that in the real world to make money or to reach so
That's I think that the question was DeepMind hasn't made any money. Is that right? Yes, that is true. From what I understand, Google bought DeepMind and then they sold them because they couldn't really make any money off of the things. And I think it's true there isn't a lot of money in beating video games, but it's a technology that's in its infancy. And I think this is the way that artificial intelligence is headed. There's so many applications for reinforcement learning. Actually, I think they used it to save Google on their power bill for their data centers. So yeah, I mean, I feel like there are a lot of companies that are doing great things where people can be short-sighted, like they'll sell their stock because they're not producing results this quarter. So, but you're right, DeepMind to date hasn't made very much money.
Actually, DeepMind has had part of DeepMind went into the medicine part. So they've actually done something about.
Oh, the protein folding?
No, they've done something about breast cancer detection.
Oh, okay.
Which is a recent breakthrough that came up.
Okay. Well, thank you.
So it's like a spell checker for images of breast cancer.
Oh, well, that's interesting. Okay.
They make money by asking billionaires for the money by doing a cool thing.
Yes. But if I were a billionaire, I would give them money. Yes.
Maybe this is too complex, but again, if you can train the computer to go and beat a bunch of DOTA players, can you basically say, this is the stock market, you're competing against all these people, go beat them?
Beating the stock market is a very common use for a reinforcement learning algorithm. I've thought about doing it myself, but I haven't done it. So yes, there was a hand over here. Yes, sir.
So Epsilon is something that we as a programmer would set, but it seems like in AI, the whole point is to let the program and the algorithm do a whole bunch of things itself. Is there a reason that we don't have the AI set Epsilon and optimize it for whatever its current task is, rather than we do that ourselves?
That would be like letting a child pick its own allowance. It's that's a very good question. It's you want some control over what the agent does, because they're not very smart at all. I mean, if you give it a reward for just bumping into a wall, it will bump into the wall for all eternity. You want it to, like I said, if there's like if there's a cake generator on the ground here and it generates like a tiny slice of cake every like 5 minutes, and you don't put an epsilon, the computer is going to stay at this spot forever, waiting for more cake. But if you do give it an epsilon, then it's going to, you know, explore until it gets to the goal that you want it to and maximize all of its rewards. So
There are curiosity-driven algorithms, right?
I've
100% curiosity.
heard things about curiosity-driven.
Play the Atari ones and stuff. It's like it's always in that mode of exploration. They can win all the Atari games as well.
Yeah, you know, as for why you wouldn't have the computer set its own exploration, I'm not sure. I mean, we can look it up afterwards if you like. Yes, sir.
Again, I keep returning to the example, but how many people look at this and saying, if you can go out and beat people, can you go out and beat a criminal, beat a terrorist, figure out their strategies and how to catch them?
It's a really good idea.
I mean, I'm worried about it being weaponized, and that if we can use it, terrorists can use it, and governments can use it to say, well, our enemy are dissidents who will protest against
Yeah,
us.
that becomes terrorist.
That would be interesting to run simulations of a protest. My thought sort of like that is, let's say you are a group of 4 soldiers in a foreign country, and you're walking down like an alley and you don't know what's on the other side. You could stop, you could press a button on your computer and it would run simulations, adversarial simulations, and say, okay, if there are bad guys there, this is where they're going to be hiding. And this is what they're going to do, so you can counteract that. And it would say, okay, this could be your strategy. I was thinking that would be a really cool application for reinforcement learning in the real world. So, any other questions?
Is there, sorry.
Go ahead.
Just on that, this was, I think, 2015, maybe 2016. There's this game where, I don't know what it's called. Basically, you play like as the mayor of a politician.
Sim City?
Yeah, that's what it sounds like.
No, it was more, you don't really do anything but choose actions. There's no like 3D model of like people or anything.
Okay.
I think someone did a very similar approach with a very basic AI, and when a protest happened, it just killed everyone.
Wait, say that again? Oh, okay.
Yeah.
Yes,
I
yes.
was like, God, bye.
That's bad.
We don't need you.
Okay.
Well, the goal is to get rid of protests.
Yeah, bad reward.
Okay, so that's a good point. Ever since the word robot was invented, which I believe it was invented in a Czechoslovakian play in 1929, that play was about robots rising up and killing everyone. So this whole fear of, you know, robots rising up and killing everyone is not new. Everybody's been afraid of it for a long time. I don't think it's going to happen unless somebody makes a really huge error in programming. So yeah, I mean, like video games can theorize about what an AI would do, but I mean, we can always program it well. Like I heard about a paper recently that said if we want AI to act more like people, then we need to make it fear death. And that is a horrible idea, because if AI fears death, then you can't turn it off. Like, I mean, can you imagine, like, my computer doesn't want to be turned off? You know, if I buy a new computer, my computer's going to say, I can't let you do that, Dave. And, you know, I mean, okay, so.
So say that's being turned off as sleep and not death, whereas death is destruction.
No, anything.
Take the battery out.
What?
Take the battery out.
Yeah, well, yeah, same thing. But yeah, so I mean, that's my opinion. As long as we are smart about it, we're not gonna have robots kill us. So yes, sir.
So, in adversarial network or adversarial,
Yes.
learn that the machines try to fool each other while they learn,
Mhm.
copy smarter. Will this reinforcement learning have anything to do with adversarial?
Yeah, in a way, yes. So adversarial networks are when you have 2 different deep learning networks. Like there's a website called, I'm going to show it to you real quick. There's a website called thispersondoesnotexist.com. This person does not exist website. There we go. And so what this does is it creates faces of people that have never existed. See this person, she has never existed. This was created by a computer. And how it does this is it has 2 neural networks. one is responsible for creating images of a human face, and then another one is responsible for saying, that's crap, that's not a human, give me another one that's better, right? So you've got a creator and a discriminator. And that's how you make something beautiful like this, something that looks real, is you have two neural networks in the mix, right? So with reinforcement learning, there is only one neural network, but it is playing against itself. So it is adversarial in nature because it's learning by fighting itself, but it isn't two different networks like this. Any other questions? Yes.
Is there a negative use you're most worried about?
For reinforcement learning?
Yeah.
I mean, just like anything, there are positive and negative uses for this. I think warfare would definitely be a negative use for this. I thought about it. I heard about a paper earlier today. I haven't read it. It's called How to Create a Malevolent AI. And I'm interested in reading it just because it's interesting, but I mean, it's a very powerful tool and there are tons of ways that it could be misused. Anytime you want information about an enemy, you could use this to figure it out. So, all right, any other questions? All right, thank you guys so much, and feel free to come up and say hi afterwards.